36.5 is on dummy variables and logistic regression. A dummy variable is a variable that only has the values of 0 and 1, and they can be used to represent the two different categories of a qualitative variable. And they can be used in linear regression as such. This example right here is a table adapted from the dataset 6 family heights, and it is a more convenient format for this example. Using the dummy variable of sex coded as 0 for female and 1 as male, given that the father is 69 inches tall and the mother is 63 inches tall, we want to find the multiple regression equation and use it to predict the value of predict the height of a daughter and a son. So for this, if we were to do so, we would have that the height of the child would be equal to 36.5 minus 0.0336 times the height of the father plus 0.461 times the height of the mother plus 6.14 times the sex. So for predicting the height of a daughter, this would be replacing then the height of the father as 69. So this would be 36.5 minus 0.0336 times 69 plus 0.461 times 63 plus 6.14 times 0. Tossing that into a calculator would give us an answer of 63.2 inches for the predicted height of a daughter. And the only difference between the one for the son is that this 0 here is a 1. So y hat is equal to 36.5 minus 0.0336 times 69 plus 0.461 times 63 plus 6.14 times 1. Tossing that into a calculator gives us an estimated value here of 69.4 inches. So as such, notice what happens there based upon that dummy variable we put in for the sex. So the dummy variable is a response variable. This in terms of logistic regression. This is a procedure used for finding a regression equation where the response variable is a dummy variable. The examples are occurrence of a disease, hospitalization, death, transplant, etc. coded as a 0 and a 1. We can use simple logistic regression when the following conditions are met. There's a single predictor x variable, sample y data have values of 0 and 1, yields the following equation format. The natural logarithm of p divided by 1 minus p is equal to b sub 0 plus b sub 1 times x. So on the right side gives us a value v, where v is equal to b sub 0 plus b sub 1 times x. For this, we would use the regular linear regression to find this. To find this particular equation, p is equal to the probability of y is equal to 1. And we could solve for p by evaluating. P is equal to e to the v power divided by 1 plus e to the v power, where v is b sub 0 plus b sub 1 times x. So for example, use the paired height gender data from the data set 1 body data set to find the simple logistic regression equation and let the response variable be gender, with 0 equals female, 1 is equal to male, and then find the probability that a person with a height of 190 centimeters or 74.8 inches is a male. So if we were to use the linear regression with that in order to find the equation, we would have the natural logarithm of p divided by 1 minus p is equal to negative 40.6 plus 0.242 times height. And if we put that 190 centimeters in, so height is equal to 190, this will give us a value for v of negative 40.6 plus 0.242 times 190. This gives us a value of 5.38. And so for p would be equal to e to the v divided by 1 plus e to the v power. So this would be e to the power of 5.38 divided by 1 plus e to the 5.38th power. Tossing this into a calculator gives us a value of 0.995. And so because of that then, the probability of being a male is 0.995. So probability of a male is 0.995. And that's a very bad 5. Let me very quickly fix that. .995, and we would obtain this graph if we were to graph it out. The multiple logistic regression equation now. This is a dummy response variable and more than one predictive variable. Again, we would use the linear regression to find the right side of this, but it yields predicted values of y. Natural log of p over 1 minus p is equal to b sub 0 plus b sub 1 times x sub 1 plus b sub 2 times x sub 2 plus all the way up to b sub k times x sub k. P is equal to the probability of y is equal to 1. Again, for this right side, we are using a regular linear regression. And that right side is equal to v. So v is equal to b sub 0 plus b sub 1 times x sub 1 plus b sub 2 times x sub 2 all the way up to b sub k times x sub k. And then solve for p. P is equal to e to the v divided by 1 plus e to the v power. So let's say, for example, the sample data set consists of the height, centimeters, and arm circumferences in centimeters of women and men as listed in the data set 1 body data set, and let the response variable represent gender, 0 for female, 1 for male. With this list of genders, heights, and arm circumferences, logistic regression could be used with software to obtain this model down here. Natural log of p over 1 minus p is equal to negative 40.6 plus 0.242 times height plus 0.00129 times arm circumference. And in this expression, p is the probability of a male. So the value of p close to 1 indicates that the person is likely a male. Close to 0 indicates the person is not a male, which is female. And for this, we could put in some numbers. Alright, so let's say, for example, we use, let us see here, let us use a height of 183 centimeters an arm circumference of 33 centimeters. We would find the p-value. Not p-value. We'd find the value of p. We'd find the value of p if I don't go leave the presentation during the middle of it. We would find the value of p, and let me just... It's not going to let me erase that now. Lovely. We'd find the value of p then to be... Take this back. We find the value of p. Once we put these numbers into the equation, solve for v, and then solve for p, we will get ourselves a probability of 0.977, which gives us the probability of 97.7% chance of being male. If we find and that's for a relatively big person. For a smaller person, let's say a height of 150 centimeters, an arm circumference of 20 centimeters. The probability of that would be 0.014, which would give us a 1.4 probability of being male. And in this particular example, researchers were interested in determining whether distortion product autoacoustic emissions DPOAEs were a useful tool for identification of hearing impairment in newborns. The dummy response variable was hearing impairment. 1 is impaired, 0 is not impaired, as defined from a gold standard test when the infants were at least 8 months of age. The multiple logistic regression model included DPOAE, continuous variable, age in weeks, sex as 0 for female, 1 as male, as predictive variables. Use of the multiple logistic regression yielded the following model based on data from identification of neonatal hearing impairment by Norton et al. In Ear and Hearing, Volume 21. Natural log of L of P over 1 minus P is equal to 3.84 minus 0.06 times DPOAE plus 0.02 times sex minus 0.02 times age. And in this table down here, DPOAE has a p-value of less than 0.01, so this one is significant. Sex and age both have p-values well above any form of significance level. So because of this, sex and age are not sufficient predictor variables. So DPOAE is a sufficient predictor variable. And if I could spell correctly, that would be helpful. So sufficient predictor variable, while sex and age are not. Or not sufficient. Let me know if you have any questions or concerns. Thank you.